so far we've essentially been looking at the problem of source coding, right? Where the goal is we have some kind of a source drawn from some distribution. So we model the source as a random sequence, and the goal is to represent this sequence is in as few number of bits as possible, right? And we look both at lossless compression, where we want to reconstruct the source sequence exactly, and lossy compression, where we only want the reconstruction to be close to the actual source sequence, right? So now we look at the complementary problem, which is that of channel coding. So suppose you have some kind of a source or a message that you want to transmit through a noisy medium. How do you do that? And if so, at what rate? We'll define what rate is. What is the maximum number of, or what is the best utilization of resources that you can do while transmitting through a noisy medium? All right, so that's the objective of this problem of channel coding. But before we get into that, let's look at at least a high level block diagram of what a typical digital communication system looks like. Right? So in the end, we want to transmit a signal or a message through a noisy medium. And the way we will model this noisy medium is that this noisy medium is some kind of a random object. It takes something as input and it outputs a random sequence as the output. Okay. So what does a standard digital communication system look like? Let's take the example of, say, voice communication. Right? You pick up your cell phone, you dial a number, and then you speak to somebody. All right. Now this is a very complex system. There are a lot of things that go on, but at the core, essentially at the physical layer of this particular communication system, something like the following would happen. Again, this is a very coarse representation of the system, but it still highlights the important parts that is relevant to us. So let's say we have, say, speech signal. All right, so speech is a continuous time signal, and the amplitude is also continuous, right? So you have the speech signal, which is continuous time, continuous amplitude, and let's say in your cell phone, the first thing that happens to this is it gets sampled. So this is sampled to give a discrete time but continuous amplitude signal. So you get the sampled signal, which is then digitized. So you have this, you can model this sampled signal as kind of a vector or a sequence of real numbers, and this is now converted into typically into a finite number of levels, or more generally it's converted to a sequence of bits. So this is analog to digital conversion or quantization. So at the end of this, you get a sequence of symbols. Typically in a simplistic system, basically the output of the analog to digital converter would be that instead of getting a sequence of real values, you get a sequence of, again, values, but within a finite number of levels. So the alphabet over here, the alphabet from where each of these symbols is drawn is infinite, it is R. at the output of the analog to digital converter, the alphabet now becomes finite. All right, maybe for example, if it's a let's say 5-bit analog to digital converter, then there are 2 to the 5 possible levels that the output can take. All right, so it looks roughly the same, except that instead of continuous, it's the amplitudes are now discretized. And then you typically have some kind of a compressor which I'll call source coding, but in principle both of these can be combined together to one source coding block. In earlier systems, what used to typically happen, in fact it still happens very frequently, is that this process of analog to digital conversion and compression is usually made separate. So you first quantize and then use some kind of a lossless compression scheme to compress it even further. All right, but in principle you could design both of these jointly, because in the end this whole process, what you want to do when you combine both of these blocks together is that you want to do lossy compression. Right, so you have a vector or a sequence of some particular length, and you want to represent this using as few bits as possible. So this put together is a lossy compression problem, but in practice, many a times you do the analog to digital conversion separately, where you do quantization and then you separately source code the sequence. All right, use something like an arithmetic code, for example. So now at the output of this source coding block, what you have is a sequence of bits. All right, let's call this mk. Maybe it's a sequence of k bits. You take a speech signal, which is of maybe some finite duration, let's say a millisecond or so, and then this is sampled, quantized, and then compressed to get this sequence of k bits. And once you get this sequence of k bits, this is typically fed to a channel coding block. All right, where the goal is to intentionally add some kind of redundancy into this particular system. Right? We'll see why redundancy and how it helps, but this is just to give the big picture. So the output is, let me call this Cn. So it's a sequence of n symbols. Typically, if you take a standard cellular communication system, Cn will be a sequence of bits. All right, where this n, the number of bits n, is going to be larger than k. All right, so you have this channel coding block. Now in the end, up to this particular point, you've taken the speech signal, which is a continuous time signal, and then you got a sequence of n bits. Now you can't just transmit these bits in the air. They have to be appropriately converted to a form where you can transmit, let's say using an antenna, or if it's a wireline communication system, that you can transmit over the wire. All right, if it's, let's say, something like a fiber optic system, you have to convert that to a sequence of optical signals. So this is usually modulated. This modulation block itself encompasses multiple sub-blocks, but the goal of modulation is to take this sequence and convert it to a form which can be transmitted over the physical medium. All right, I'm going to put all of those together into this single modulation block. If you've taken a digital communication course, then basically this modulation block would convert the sequence of symbols into a sequence of, let's say, IQ symbols. So you have a sequence of bits. These are converted to the corresponding IQ symbols, and then modulate it using some kind of a carrier signal which can be transmitted. And this modulate, and the output of the modulator is typically some kind of a continuous time signal. All right. So this would be some kind of a continuous time signal, and this is fed to the physical medium. So if this is a cellular communication system, then the output of this modulation block goes to the antenna, and that is transmitted. Right. Again, this by modulation, I assume that there's a lot more that goes into it. For instance, this has to be amplified sufficiently, and then the carrier has to be added, and so on. At the receiver, you essentially have all of these blocks in reverse. So you receive the output of the channel goes into the receiver, which is another cell phone maybe, or a base station, and the base station typically takes the physical signal, which is a continuous time signal, and now this is demodulated. Let me call this YN. All right. Just to be consistent with notation I will use later on, I'll call this XN, what is sent to the input of the modulator, as XN, and the output of this demodulator is going to be YN. And now this is given to the channel decoder, and again it depends on exactly what the output of this demodulator is going to be. In some systems, this would be a sequence of bits, but sometimes it need not be the sequence of bits. It could also be, let's say, a sequence of real symbols. All right, and we'll see that in a little bit. So the output of this channel decoder is something that I call is another k-bit sequence, which is going to be decoded by the source decoder. Essentially, it's going to be decompressed. The source decoder is going to output a sequence of symbols, all right, which is then fed to, let's say, a digital to analog converter, and then you reconstruct this to give your continuous time speech signal. All right, so this is what a standard digital communication system looks like at a high level. All right, it doesn't matter which generation, whether you're talking about 2G or 4G or 5G. At a very high level, this is what happens in all of them. All right. Again, here I've given the example of something like a speech signal. If, let's say, you want to transmit files, for instance, you want to download a YouTube video perhaps, then the system would look a little bit different. You don't need all of these blocks. For instance, all of these sampling ADC is not required, because the goal is to transmit digital signals itself. In this case, we've taken an example where we want to actually transmit an analog signal, which is speech. All right. Any questions? How many of you have already taken a course in digital communications or so? Okay, so good fraction, but not everyone. So at least some of you are already familiar with something like this. For others, this is just, this is how things work. All right. Now, so this physical channel is something that takes as input signal. You think of it as some kind of a black box, which takes the signal that is transmitted from the antenna and outputs another signal which comes to the input of the receiver antenna. All right. But more generally, what we will do is we will combine all of these blocks together and call this kind of something like a logical channel. We just combine all of these blocks together and put together, we will call this the channel. And I call this the channel from the perspective of the channel coder and the channel decoder. All right. Now, there's something to be kept in mind. I drew these several blocks, right, each independent of the other. Now, if you think about it, a natural question that comes up is, well, why do you want to separate out all of these blocks? If the end goal is to design a good communication system, wouldn't it be more optimal to combine all of these blocks together into one single block, which takes as input a continuous time signal, and combine all of these blocks together, which is a receiver block, which takes as input the airwaves and outputs a reconstruction of the original continuous time signal? That's a natural question to ask. And in fact, doing that could potentially be more optimal. But separating out these basic blocks has several operational advantages. For one, you can just design each of these blocks separately, and you can change the blocks as and when you want. For example, you can keep all of these the same, but change only the channel coder based on maybe the characteristics of the channel. All right. Similarly, you could keep everything else the same, but maybe only make changes to the source coder. Maybe someone comes up with a new compression scheme, then all you have to do is just replace this particular block while keeping the rest of the blocks unchanged. So this kind of a modular structure has several advantages. And more importantly, what it is also known that under certain mathematical assumptions, there is no loss in splitting this problem of compression and channel coding. All right. So whether you combine the blocks together or separate them out, it doesn't make a difference, because combining them cannot, if you design both of these optimally, if you take the optimal source coding scheme and the optimal channel coding scheme, then it will do as well as a scheme that combines all of these together. All right. I'll make all of this a little more precise, but this is just to give you a preview. Okay. So far we've at least among you who've taken some basic courses on signal processing and digital communications, and part of what we've seen in this particular course, you know what each of these blocks look like, right? You know how to do sampling, and so far we've seen some basic lossy compression. Okay, so we have some idea of what these blocks look like. The goal now is to essentially open up this particular block, see what happens in the channel coding and channel decoding blocks. All right. So let's go ahead and do that. So, but before we go ahead and try to design these blocks, the most important thing to do is first mathematically model the system. All right. So our goal right now is to essentially just design these two blocks. So everything else is kept fixed. You cannot change or modify any of these blocks. and you are given the task of designing the channel coding and the channel decoding blocks. Okay. So if we are to design that, let us see what is the input to this block and what is going to be the output of this particular block. All right. So what is the channel coding problem? The channel coding problem is the following. So we have this sequence, this bit sequence MK. So it's a sequence of k bits. The goal is to encode this or convert it to a sequence of n symbols which is fed to a block which I'll collectively call the channel. I'm sorry, this should be xn. And all of this basically happens at the transmitter. At the receiver sees a sequence of n symbols, which I'll call yn. So we want to design this decoder, which outputs an estimate of the message. The end goal is to model this medium. The first step is to give a mathematical model for this so-called channel, which is reasonable and which we can work with. And then, given this model of a channel and certain other constraints, the goal is to design this encoder and decoder. All right. So first, let's think about what a channel may look like. All right. What do you think? What could be a good description or a model for a channel? You can come up with anything you want. Yeah? Okay, just that? We're missing out, I guess, one of the most important parts. Noise, right? So one way of modeling is, let's say that the input to this channel is a real number, say. The output of the channel could be the signal, the main impairments that one sees are noise and some form of attenuation. There are many other factors that come in, but that's those are the most simplistic forms of channel impairments that one can think of. Right. Now let's take a step back and try to think about what we can do in order to mitigate this. Right. So let's go back to let's say the 1950s, 40s, and 50s, and you had to design a communication system. Of course, at that point, you didn't have digital communication system. Everything was analog, right? So you have these signals, let's say speech signals. How do you transmit speech signals across very large distances? Right? That was a fundamental problem. And remember, all you have are analog communication systems at that particular point. So what would be the most obvious thing to do? Or what do you suggest?
Send over small distances and then amplify themselves.
Great. So that was precisely the idea that was used in the early telecommunication systems. Basically, you use what are called repeaters. So if you want to transmit over, let's say, 100 kilometers, then maybe every 10 kilometers or so, you introduce a repeater. Mind you, at that point, it could still be a wireline communication system. So all of this communication is going to go through wires. So you have control about where you can place repeaters and so on. It simplifies things because you don't have to worry about things like interference and so on. So think of early landline communication systems, where everything is happening through wires. Even though you're transmitting through wires, you still have the problem of attenuation and noise, right? So the early idea was, well, you put a repeater in between. But then repeaters have a certain problem, which is that if you amplify the signal, then you're also amplifying the noise, because the input to the repeater is going to be a noisy signal, and all the repeater does is just amplify the signal. So it's going to also amplify the noise. So eventually, when you go from the transmitter to the receiver, the final receiver, you have a signal, so the attenuation is kind of taken care of, but then the noise gets amplified at every basically repeater, and in the end what you have is a signal that has decent signal strength but a lot of noise. All right? And the noise not just comes not just from the medium, but also the receiver system itself. All right? In general, most of the noise comes from receiver noise. So the receiver noise itself, so the receiver typically contains some kind of a circuit, which is usually a low noise, some kind of an amplifier, and this also introduces some noise, which can be a major component. So every time you are introducing a receiver, you are also introducing some noise into the system. All right. So now, if you had to do pure analog communication, then you run into this fundamental bottleneck. You cannot transmit over very large distances. So introducing repeaters only makes the noise even worse. All right. So then what do? What is the other solution? Suppose now that you moved from analog communication to digital communication. Can you use the same approach to do something better? So let's go back to the analog communication system with repeaters, right? So basically you have this transmitter and you have this receiver. Now you want to communicate over this large distance. Instead of sending it all at once, which would cause a lot of attenuation, what you can do is you put repeaters. This is the first repeater, the second repeater, and so on. Okay, so this takes care of the attenuation, but introduces a lot of noise. That's the fundamental problem over here. And we are, for now, when I'm talking about a repeater, we are thinking about a purely analog system where the repeater is essentially just an amplifier. Think of it as just some amplifier. You can maybe do some basic filtering, but there's a limit to how much noise you can remove out of the system. So that's one fundamental problem of the analog communication system. But if you were to replace this analog communication system with a digital communication system, could you do better conceptually? Do you think there is hope of doing better? So we don't know what error correction is at this point. Okay, we are going back to the 1950s, where the concept of error correction and the concept of parity was not known. Sorry?
Low pass equivalent.
But that's still an analog system, right? So my fundamental question, the fundamental question that I'm asking is the following. Why does digital communication help over analog communication? Why can we hope to do better? As opposed to using a purely analog system, right? Because if you think about, let's say, our cell phones, these are purely digital systems. All of the communication happens digitally. And except in very specific cases like AM and FM or FM radios, for example, most of the communication that you see is digital. So why digital?
There's only two, like there's only 0 and 1.
Okay, so there are finite number of levels, all right? So it's discrete, but why should that help?
It'll be easier to decode. The
Easier?
physical factors are like abstracted away. You just have to.
Okay, physical lab, but how does that help again? Maybe let's try to put this in the context of this specific scenario. You want to communicate over very long distances. Why would digital help? Again, let's not think about like how modern communication systems work. Let's go back to the early days where you had to design something from scratch. So would there be an advantage of moving from analog to digital systems? And why would that help? But again, why will that help?
You could take
But when you're doing that, right, you're losing information. You have a continuous time signal which has to be represented using a finite number of levels, which automatically means that you're losing out information. It's an approximation, right? So why should that help? Yeah. Any other answers? Okay. So basically, look, when I say I'm going from analog to digital, right, it means that if I had to transmit digital information, then firstly, I have to represent my continuous time signal into a discrete number of levels, which means I'm losing out information already because of this discretization, because of digitization. So the digitization process itself leads to some loss of information. But even then, we are still using a digital communication system. Why?
That is enough to reconstruct.
Okay, it's enough to reconstruct, but how does that fundamentally help us solve this problem of communicating through a large distance? Because the noise is still present. Ultimately, even if you represent your source as a sequence of bits, in the end, when you have to transmit it through the channel, it has to be represented as a continuous time signal and then transmitted, right? So how can...
exact question, why are we doing this?
Yeah, why do you think representing using a finite number of levels would help? Why is it easier, or why is it better to transmit digital data over analog? There are many reasons, of course. For example, the design of hardware and stuff. But let's not go into that. From this perspective of designing the communication system, why would designing a digital communication system, again, from with focus on noise and recoverability, be better for digital communication systems than analog?
Because you can make proper decisions on as to like what is to.
Okay,
So
the
if you
close.
attachment, you could say like this is maybe 1
Okay, that's close. So basically what you could do at these repeaters, right? Earlier in our analog communication system, the repeater was essentially just amplifying whatever was received. So it was amplifying both the signal as well as the noise. All right. Now let's suppose that each of these links introduces a certain amount of noise. If the number of levels were finite, then instead of just blindly amplifying, what you could potentially do is decode at each step, right? Because the signal that you're transmitting is digital, effectively it becomes a decision problem, right? So instead of transmitting, say, a real number, you're transmitting one bit. So at each of these repeaters, basically the repeater has to decide whether the transmitted symbol was a 0 or a 1. All right. So even if there is some amount of noise, right? Suppose that there's a small amount of noise that is introduced in each of these links. If the level of noise is small enough, then you can reliably say whether what was sent was a 0 or a 1, right? And if this repeater was able to correctly decode whether the transmission was a 0 or a 1, then it is as though you got rid of all of the effects of noise up to this particular point, right? Because at the output of this receiver, you have a clean signal. It's 0 or 1. Unlike the analog communication system, where what the repeater 1 was transmitting had both a signal component as well as a noise component, right? So, in principle, what you could do is, if you keep too many repeaters in between, even though there is some noise introduced at each of these links, you could get rid of that noise. Right? Conceptually, it would be very expensive to do so, that's a different story. But in principle, you could transmit a clean signal from the transmitter to the receiver by introducing a huge number of repeaters. Right? And that's a fundamental advantage of going to digital communication instead of analog communication. Right? So this is an extra resource, mind you. I have to put a repeater at a huge number of intervals. All right? But if you have a purely digital communication system, then what you want to recover is not a continuous signal, it's not over a continuous range of amplitudes, but over a finite number of levels. And potentially you can reduce the effect of noise by decoding at each step. Right? So maybe to give a concrete example, in the case 1, so purely analog, right? You have a number x, which is, think of it as a single real number that you want to transmit, right? And the overall amount of noise that you will introduce from the transmitter to the receiver is going to be fixed. You can't change that. If you, again, this is a very, very simplistic model, but let us suppose that if I introduced a large number of receivers in between, then that noise would kind of get distributed, right? So if I put many more receivers, then the amount of noise over here in each of these would be small, but the overall level of noise would roughly be the same. Okay? Again, it's a very, very simplistic model. It's a toy model essentially. All right? So then what would happen? The output of receiver 1, you would get some attenuated version hx plus, let me call this z1. So receiver 1 sees hx plus z1, all right? Or let me call this h1x plus z1. So in a purely analog communication system, the repeater 1 would just amplify this. Maybe it knows the attenuation level exactly, all right? Then receiver 1 would output x plus, basically it would multiply this by 1 by h1. So it would transmit x plus z1 by h1. Right? Think of h1 as some small number. Right? So it would transmit x plus z1 by h1. So 1 by h1 is going to be a large quantity. Right? So now this is sent to the second repeater. The second repeater gets h2 times what was transmitted by repeater 1. Right, so it gets h2 times the signal transmitted by repeater 1 plus some noise. Now what repeater 2 can do is basically amplify again. So maybe it sends x plus z1 by h1 plus z2 by h2. Basically, it multiplies by 1 by h2. Right? And so on. This is basically what each repeater does. Okay. So essentially at the final receiver, after whatever correction or amplification, the receiver can essentially output x plus z1 by h1 plus z2 by h2 and so on. So if there are m repeaters, then it would get plus zm by hm. All right. It's a very simplistic model, very simplistic behavior, but think of this as some kind of rough back of the envelope kind of model. Okay. So the more repeaters you introduce, the noise being whatever you do, you can never get rid of this noise. All right. And effectively, if you introduce more repeaters, then you're boosting up the noise every time. All right. So it's clearly not a good approach. On the other hand, let's see how digital can potentially help. All right, now suppose that x is just a single bit. It's either 0 or 1. Well, at the end, what do you want? You want to reconstruct x. But what you actually get is x plus a whole bunch of noise terms. And there is no way you can get rid of these noise terms. Right? So, and the more repeaters you introduce, the more noise terms there will be. And there are many sources of noise, right? So one is coming from the channel itself. The other is in the receiver circuitry. So the more number of repeaters you introduce, the more analog circuitry you require, and each of those will introduce some amount of noise. So the overall noise will increase. All right? You get rid of the attenuation, but now you introduce a lot more noise into the system. Right? Any questions? Great. So now let's contrast this with a digital approach to this problem. Okay, my x, which I had, is maybe quantized into a certain number of levels. For now, let's just assume it is quantized to binary, 0 or 1. All right, or maybe if you want, plus 1 or minus 1. So I've taken the signal, I quantized it into a discrete number of levels, and now I transmit this. So now at receiver 1, maybe it gets h times x1 plus z. As before, the communication system, at least the channel behaves, the physical medium behaves exactly as before, nothing else. So it gets h x1 plus z. Now instead of just amplifying, what you could potentially do is decode. Right? So remember, you have two levels, right? And what you receive, maybe you transmitted plus 1, and you had some amount of attenuation, right? Maybe the attenuation was, I don't know, 0.1 or something. And maybe the level of noise is small enough. Okay, maybe 0.01. That's the variance of noise, perhaps. Much smaller than h. Okay. In that case, you still may be able to say whether what was transmitted was a plus 1 or a minus 1. All right. So, for example, if you just had to cook up some numbers, maybe what you transmitted was 1, maybe the value of h is 0.1 plus the noise, which is, I don't know, maybe minus 0.01. All right. Now instead of, if you amplified and transmitted, the problem was the noise terms keep accumulating together. But now here's a better solution. Let us decode, which basically says put a threshold. So if what you get is greater than 0, you declare that as +1. If it is less than 0, then you declare that as -1. All right. Now in this case, in the scenario where the noise level is very, very small, you can still recover what was transmitted. So this would be decoded to +1. All right. And now you can transmit this +1 from repeater 1 to repeater 2. But now contrast this with the analog communication system. At this point, because you decoded that 1 correctly, you got rid of all of the noise up to that point. Right? There's no effect of noise anymore. Now, if this were decoded to a -1, then you would be in trouble. Right? But as long as that doesn't happen, it's as though you're starting fresh. All right? And now this can keep happening at each repeater. So at, let's say, the ith repeater, if you have decoded correctly, then it means that all of the noise that was there up to that point doesn't really matter. You got rid of all of that. But over here, you can never really do that in this analog communication system. You can never get rid of the noise completely. There will be some effect of noise. And that will keep accumulating, and it will accumulate the more number of repeaters you include in the system. So at least in this digital repeater system, if you introduce a huge number of repeaters so that the noise level at each repeater is not too large, you can potentially transmit reliably from the transmitter to the receiver. There is hope. All right. But of course, this method is very, very expensive because you need to put in a huge number of repeaters. All right. Any questions?
What is the worst case possible?
Yep.
You can accumulate. Is the worst case possible here better than worst case possible?
It depends. It's a little more nuanced than that, right? Because it depends. Because again, if you think about it, if you make an error at one point, then that's going to propagate forever, right? And the more number of repeaters you put in, you can do some rough calculations. This will also, it's not a perfect system. So unless you know that the noise level introduced at each stage is going to be very, very small, you can never really get rid of it. All right? But again, we'll use a completely different approach. But all of this is just to motivate the point that there is a lot of advantage in going from purely analog to a digital system. All right? Because a digital system can get rid of some of these nasty effects of noise. In an analog communication system, there is no hope of getting rid of that noise. Whereas in a digital communication system, there is hope. If you decode correctly, then you got rid of all of the noise. All right? Okay. Now, note that whatever you do, right, there's always a trade-off. Always giving something up for something else. All right. So now, how do we model this? Okay. So even before that, so let's now come to the new approach, right? So, and this was what was proposed by Shannon in 1948. So until now, our basic communication system just consists of repeaters. And our goal is to do something so that we can get rid of these repeaters. I want a transmitter and a receiver, but still I want reliable communication between the transmitter and the receiver. All right. So what do we do? So one approach is, okay, let's first consider a mathematical description of this particular channel. Okay. So the channel we'll assume that this channel takes as input a sequence xn, an n-length sequence xn. and outputs a random n length sequence yn. We'll assume that xn comes from some alphabet. It could be real, it could be complex, it could be a finite alphabet. All right, and this x is called the input alphabet. For example, the input alphabet could be binary. The input alphabet could be the set of reals. It could be the set of complex numbers, doesn't matter. But one thing to keep in mind is that right now I'm assuming a discrete time system. Okay. Just for simplicity, but all of this can be extended to continuous time systems as well. Okay. And the output of this again comes from some alphabet, which is called the output alphabet. Again, the output alphabet could be binary, it could be the set of reals, it could be set of complex numbers, it doesn't matter. All right. And the channel is modeled as a random black box. And it's described by some conditional distribution Pyn given xn. So the channel takes an input, some sequence xn, and outputs a random sequence yn according to the distribution Pyn given xn. Okay. So for us, whenever I say, so henceforth, when I say channel, it means that it is this black box which takes a sequence and xn and outputs a random sequence yn. And for now, we will assume that this Pyn given xn is known to us. All right. And at least for now, we will, in this course, we'll only focus on the so-called discrete memoryless channels. Abbreviated as DMC, which is this discrete, essentially means discrete time, and Pyn given xn is just the product So basically, if you transmit n symbols, then the channel app operates on each symbol randomly and independently of all of the other symbols. All right. So, for example, if you're transmitting a sequence of bits, then what the channel does is basically each bit is corrupted independently of all of the other bits. That's what I mean by a discrete memoryless channel. So the way the second bit is corrupted doesn't depend on how the first bit was corrupted. And the distribution of corruption for each of these bits is the same for all of the bits. That's what I mean when I say discrete memoryless channel. Okay, so let's take some examples because we'll frequently revisit each of these. The first is what is called the binary symmetric channel. Which is abbreviated BSC, and it has a parameter P. So I'll say BSCP, and this P is called the crossover probability. And what this basically does is, if the input to the channel is a bit, either 0 or 1, the channel flips this with probability P, and it keeps it as it is with probability 1 minus P. So the probability that y is equal to x, or should be more precise. So py given x of 0 given 0 is 1 minus p, and py given x of 0 given 1 is p. Okay. Sometimes it's helpful to pictorially represent the channel using this channel transition diagram. So the input is either 0 or 1, the output is either 0 or 1. If you transmit a 0, then you get a 0 with probability 1 minus p. If you transmit a 1, then you get a 1 with probability 1 minus p. If you transmit a 0, you get a 1 with probability p. If you transmit a 1, you get a 0 with probability p. Okay, so this is one representation of the channel. Another representation of the channel is using a matrix. Basically, it's the same. If you describe the transition probabilities of py given x, then basically you describe the channel. And you can represent py given x in a number of different ways, either this pictorial form or in the form of a matrix. Right? Where? So basically 0, 1, 0, 1. So the rows are indexed by the symbols corresponding to x. The columns are indexed by symbols corresponding to y. And basically the values of py given x are filled in. This is another representation. Basically, it's just py given x represented in different forms. That's all. Any questions? Okay. The second example, again something that we'll frequently refer to, is called the binary erasure channel. So in this case, the channel doesn't introduce any errors as such, but what are called erasures. So this is abbreviated BEC, and again it is characterized by a parameter P, which I'll call the probability array of erasure or erasure probability. Alright, so in this case, the input alphabet is binary, exact as in the previous case. But now the output alphabet is ternary. There are 3 symbols in the output alphabet, 0, 1, and a new symbol which I'll call the erasure symbol. Alright. Again, it's as the name suggests. Basically, you write down a sequence of numbers, maybe, and what the channel does is it erases out some of the locations. Alright. So in this case, so py given x of 0 given 0 so if you transmit a symbol which is either 0 or 1, then the output is also going to be the same thing, with probability 1 minus p. And with probability p, it gets erased. Right. Now, in this particular channel, if you transmit a 0, you will never receive a 1. You will either receive 0 or you will receive erasure. If you transmit a 1, then you will either receive 1 or you will receive erasure. You will never receive 0. All right. So, if I had to write this in this diagram, it would look something like this. If you transmit a 0, you receive a 0 with probability 1 minus p, and you receive erasure with probability p. If you transmit a 1, then you get an erasure with probability p, and you receive a 1 with probability 1 minus p. So this is the erasure or erasure symbol. Any questions so far? Okay. So these are examples where both the input and output alphabets are finite. Right? You can also look at infinite alphabets. The most common is the additive white Gaussian noise channel. Right, in this case, the input alphabet is set of reals. The output alphabet is also the set of reals. And one simple description of this channel is if you transmit a real number x, then the output is going to be a real number y, which is equal to x plus z, where z is a Gaussian random variable with mean 0 and some variance sigma square, which is called the noise variance. Right. So in this case, the conditional density Fy given x, what is this going to be?
Normal with mean x and sigma square.
Correct. So it's basically Gaussian with mean x and variance sigma square. All right. So these were some examples of channels, and these three will be the channels that we will most frequently come back to. But in principle, all that we do can hold for more general channels. All right. So a channel now is basically it's just a conditional distribution. That's all. All right. Any questions? Okay. So now we have this model of a channel, right? And this is given to us. We have no way of modifying or manipulating the channel. Right? So, for example, let's keep this one single channel at the back of our mind, at least for the next couple of classes, which is the binary symmetric channel. So you transmit a sequence of bits. Some of those bits are going to get corrupted. They're going to get flipped with some probability. All right, and you have no way of changing p. P is fixed. Let's say p is equal to 0.1. So if you transmit a sequence of n bits, then what you can safely assume is that roughly 0.1 fraction of these bits, or 10% of the bits, are going to get flipped. You don't know which ones, you don't know in which locations. All right, but for n large enough, you know that roughly 10% of these are going to get flipped. You can't do anything about that. So now, given this particular channel, is there a way of transmitting information reliably? Going back to this particular block diagram, well, we have this communication system. How do we design this encoder and this particular decoder so that you're able to recover M as reliably as possible? Okay, so that is the channel coding problem. Design an encoder and design a decoder such that you can recover M as reliably as possible while making as few uses of the channel as possible. You have a k-bit message, you're using the channel n times, right? If n is large, it means that you need longer to transmit, right? So you want n to be as small as possible for a given k, and you want to make sure that mk hat is equal to mk with some high enough probability. All right, that overall is the channel coding problem. So we'll assume that it's a discrete memoryless channel, which is specified by py given x. Right, so the goal is to design this encoder and decoder such that you make as few uses of the channel as possible, and the probability of error is as small as possible. All right. So in this case, the rate we'll define as k over n. So for a given k, you want n to be as small as possible, or conversely, for a given n, you want to transmit as many information bits as possible. So you want k by n to be as large as possible, right? So in the channel coding problem, you want this rate to be as large as possible. And so, and we'll define the probability of error, sometimes also called the probability of block error, which is the probability that mk hat is not equal to mk. Right? And I'll denote this by p. Okay. So for this, we will make another assumption. I'll see if we have time. We'll also relax that assumption in this course. But we'll assume that mk, the sequence of bits, is uniform. Okay. And there's a reason why we have this uniformity assumption. The reason is because what is mk? If we go back to our communication system block diagram, mk is basically the output of the source coding block. Right? So mk is a sequence of compressed bits. And we would expect this sequence of compressed bits to be close to uniform. Why? What would happen if it is not close to uniform? Then potentially you can compress it even further, right? Which means that you are not using a good compressor. So if you use a good compressor, then the distribution of the compressed bits should be close to uniform. Otherwise you could design another Huffman code or an arithmetic code to compress the bits even further. And if you're actually compressing it close to the entropy, then the bits are going to be close to uniform. So for the channel coding block, we can safely assume that the message bits are close to uniformly distributed. But in fact, much of the theory that will develop will hold true even if they are not uniformly distributed. Right? But one thing to note is that when I say probability of block error, this is also called the average probability of block error. This probability is taken both over the choice of the message and the randomness introduced by the channel. So there are two sources of randomness over here. One, because the message is random, that is, this sequence of bits is random. And the second source of randomness is coming from the channel itself, the noise that is being introduced by the channel. Okay. So this randomness is from the source and channel. All right. So the goal is therefore to make sure that this rate is as large as possible for a target probability of error. Maybe you want the probability of error to be 10 to the minus 3. Then it means that if you transmit a k length message, maybe a 1 MB file perhaps, then what you get at the output of the decoder should be exactly that 1 MB file. All of the bits should be exactly the same with probability 1 minus 10 to the minus 3. All right, those are the requirements. Okay. Sometimes one can also look at the probability of bit error. Or the bit error probability, which is the maximum over the k bits of the probability that mi hat is not equal to mi. Let me call this PB. Now, it's easy to see that PE why is this true? Let's say PE is less than or equal to K times PB. Yeah? Okay. But remember, PE is the probability of block error, right? The whole block. So if there is no block error, it means that all of the bits are recovered exactly. Probability of bit error means maybe the ith bit is in error. Yep, it's just basically comes from the union bound. So when do you have a block error? There's a block error if at least one of the bits are in error. If all the bits are recovered correctly, then it means that the whole block is recovered correctly, right? So the probability of bit error is therefore the probability that one of the bits is in error. And the probability that there is a block error is the probability that mi hat is not equal to mi for at least one I. Right? Which is a union of the events that mi hat is not equal to mi. This is less than or equal to by the union bound. Mi, which is less than or equal to K times PB. Okay, so there is this relationship between the two. So when you design a communication system, sometimes you have a target probability of block error constraint, sometimes you have probability of bit error constraint. All right? That again varies from application to application. So for example, if you have voice communication, it's okay for some of the bits to be in error, right? Because small errors, after all, you can't really distinguish between them, because what you hear should be roughly what is said. So some amount of loss is tolerable. But for example, if you want to transmit files, all right, then you can't have even one bit being in error. That's troublesome, right? Because if you transmit, say, a zip file, and you just change one of those bits, then what you receive, or maybe a text file, if one of those bits is wrong, then it means that some of the characters could be completely garbled, right? So in such scenarios, you want to target block error probability constraint. All right. But in the end, we'll see that whether you're looking at bit error probability or block error probability, the largest R that you can achieve is the same. So the largest R that you can achieve under a probability of block error constraint is the same as, effectively, asymptotically, is the same as what you can achieve with a bit error probability constraint. All right. Okay. Any questions? Fine. So this is a good point to stop. Yeah. I'm sorry?
So like we can write 1 minus 1 minus PB whole per state.
That is assuming that the probability that mk hat is not equal to mk is IID. That's not true, right? Remember that you're introducing some form of channel coding, right? Some redundancy. If you were transmitting uncoded, that is without any channel coding or decoding, right? Then what you say could be correct because each bit is being corrupted independently with the same probability. But if you have a channel coding scheme, then you're deliberately introducing correlations between the bits, between the MK hats. So MK has IID bits, but MK hat not necessarily, right? Because you've deliberately introduced the redundancy and dependence, right?